is visible and I am also audible to all of you. So yesterday we were discussing about numerical differentiation and we learned how we calculate the differentiation at initial and last point using the Newton forward derivative formula and Newton backward derivative formula. Now we deal with the unequally spaced data. Suppose we have n plus 1 data points like xi, comma fxi, and they are now unequally spaced. It means there is like no such relation like xi equals to x naught plus ih. Such kind of relation is not available in xi's. So if we have unequally spaced data of n plus 1 data point sets, so we know that this is the formula known as the Newton divided difference interpolation formula. So like f of x naught, x minus x naught, then first order divided difference between x1 and x naught plus x minus x naught, x minus x1, second order divided difference between x1 naught, x1, x2, like this. So what we do to calculate derivative, we differentiate this equation 3.22. So after differentiation, we will get this. Like in the left hand side, it is f dash x. In the right hand side, this is constant. So this one is 0. And here only one like a linear factor of x. So if we differentiate this, we will get 1 and we will get this f of x naught x1 is remaining. Here we have like a product of two linear factors x minus x naught into x minus x1. So like we keep first as it is and differentiate second, plus we keep second as it is, differentiate first, we will get this after differentiating this with respect to x, and then this second order divided difference between x naught, x1 and x2, and we go like this for this also, and finally we have after differentiating this one. So this is the derivative formula for unequally spaced data. And here you can substitute like whatever point you want to know the derivative, whether it is a point of from the tabular value or non-tabular value, you substitute there and calculate the divided differences of all orders and substitute here, you will get the value of the derivative at that point. Similarly, if you differentiate this equation 3.2 one more time, you will get this one. And this is the second order derivative.
So normally again the classical theory, Lorentz field theory, other thing. And the second thing is this anomalous effect between the electron spin and the purely quantum. So we go in how this spinning is going on with the magnetic field, then you can see with the magnetic field, you see the one line can be creating the 5 lines. Another is 3 lines.
So this is the second order derivative using Newton divided difference interpolation formula. So it's like that instead of remembering this formula, we know that it's actually simply our Newton divided difference interpolation formula. So from there we calculate the polynomial and then differentiate with respect to x and then substitute the value of x instead of remembering this 3.22 formula. Similarly for this also. So in like these formulae are rarely used, but you have I am actually introducing these like these kind of formulas are also available. So like you have this unequally spaced data, you can see here the common difference is zero point 0.5, but here is the difference is 1. So this is unequally spaced data and we have to calculate derivative at this point. So if we have unequally spaced data, so we have to like construct the divided difference table. So divided difference table is like this minus this divided by 1.5 minus 1, we will get this one. This minus this divided by 2 minus 1.5, you will get this one. And like this you can calculate the difference, second order divided difference and third order divided difference. And the formula, you know, for the derivative like this: f of x naught x1 x minus x naught plus x minus x1 second order divided difference, and the third order divided difference. In higher order it is 0 because you have 3 plus 1 data point set, so it means a polynomial of third degree exists. So fourth and higher order derivatives divided differences are 0. Now you substitute here x equals to 1.6 in this formula, and you substitute the value of this from here. This is the value of first divided difference. You substitute here. This you substitute here, and this you substitute here, and this is like x1, x2, x3. You substitute all this, and x is 1.6. After substituting all this, you have the value of first derivative at the point 1.6. Similarly, you can use the second order or calculate the second order derivative by using the this equation 3.24. So in such cases, it is better to like find the polynomial, differentiate, and substitute the value x equals to 1.6. Or this way you can also do. So there is another formula, like it is not discussed here, but I am telling you the Lagrange interpolation formula can also be used. Like you know that for unequally spaced data, Lagrange interpolation formula, you can create a polynomial that best fits the unequally spaced data, and then you differentiate that polynomial with respect to x, and then you substitute x equals to 1.6. You will get the derivative of this tabulated value at the point x equals to 1.6. So in numerical differentiation, like these formulas are generally important to us because this one, the first divided difference for equally spaced interval; this one, the second order derivative for equally spaced data at initial point, and then the backward one, this one, and this one. And this is like an approximation of derivative that we will use when we solve the differential equations. So now we have numerical integration. So for numerical, I think this PDF is also visible. So now we go for a numerical integration. So suppose you have you don't know what is the value of fx explicitly. One problem is that you don't know the value of fx explicitly, but you know that like at x1 fx1 is this one, at x2 fx2 is this one. Like this you have n plus 1 data point sets. So if you have n plus 1 data point sets, then how you calculate this what we call the integration of a to b fx dx. Second thing is that you know the value of fx, but you have to find this integration numerically, because sometimes it is like too difficult to integrate this known function of fx. So we will actually we want to calculate the integration of this numerically instead of trying to find the solution analytically. So in that case, what we do, actually we have the already given this definite integration limits, lower limit and upper limit, So what we do, we find
So next is the
n equally spaced points within this interval a to b, and on those points, because we know explicitly now fx, we calculate the value of fx. So it means whether we know the function fx explicitly or whether we don't know the function fx explicitly, we have to deal with these n plus 1 data points.
then what happened?
So if somehow we have obtained these n plus 1 data points, then we can calculate this integration.
Minus mu.
So we'll see how to do this.
Minus mu b.
So this is known as the Newton-Cotes quadrature formula. So how we will use this one?
Mu b is the Boltzmann.
So suppose we have to calculate this definite integral a to b fx dx, or sometimes I write y equals to fx. So first job is to divide this interval a to b into n equally spaced data point, or sorry, n equally spaced interval and n plus 1 data points. Okay, so we actually subdivide. This is a one interval a to b. We subdivide this interval ab to n equal intervals, n intervals, and n plus 1 data points we will get. So we'll see how we'll do this. This is the interval AB. This is given to us. So what we do, we assume our first point is x naught and last point is xn. And in between we choose the point x1, x2, xn minus 1 like this. So you can see there x naught, if we start from x naught and go to till this xn, we have n plus 1 data points, but the interval is like one interval, two interval, and n interval. So we have subdivided the given interval ab into n subintervals. And how we choose these x1, x2, xn? According to this equally spaced relation, xi equals to x naught plus ih. So hence the integration this a to b can be rewritten using the Newton forward interpolation formula. So what you have done here, actually you have find the n plus 1 data points within the domain of the integration a to b, and you have obtained the value of yi also at all these points: y of x1, y of x naught, y of x2, y of xn plus 1, and y of xn, because you know the form of y. If you don't know the form of y, then it is explicitly, these data explicitly given to you. So if we have a polynomial y which fitting this n plus 1 data points, so it means I can create a polynomial by using my Newton forward interpolation formula. So here I have written the Newton forward interpolation formula for these unequally spaced point. Because this y is a polynomial, and for this y polynomial we have already n plus 1 data points. So I can fit a polynomial by using the method of Newton forward interpolation formula, and the polynomial is given by this equation: y naught plus p delta y naught plus p into p minus 1 upon 2 factorial delta 2 y naught, and like this p into p minus 1 into p minus n minus 1 upon n factorial delta n y naught. And what is the value of p? P here is x minus x naught upon h. So some author use the notation s instead of p, but the meaning is same whether I write s or p. It is x minus x naught upon h. So x equals to x naught plus ph, or if this is the thing, x naught plus ph, so what is the value of dx? Dx is h dp. So the value of dx is h dp. So here you can write like this: if this is the situation, like a minus x naught upon h, like if I substitute here a, integration, that is I am calculating what is x, so I am substituting x also a. So let at x equals to a, I will have this, because the relation is x minus x naught upon x minus x naught plus ph. So a equals to x naught plus ph, and x naught is still a. So finally your value of p is 0. Now for the upper limit, x equals to b, it is like I substitute b, but x naught is still a. So it is like I can say that this one is a and this one is b, and I can also write in terms of xn also, because xn is like x naught plus nh, because b is xn. So x naught plus nh, so x naught will cancel out here, and you have with us p equals to n. So when x equals to a, p equals to, when x equals to a, p equals to 0, and when x equals to b, p equals to n. So then we have this, the way we have substitute the x equals to x naught plus ph. So a to b, it means p equals to 0 to n, and then this dx is replaced by h dp, and all x are already in the form of p. So we have this one. Now what we do, we integrate this. We take this h outside here, and we integrate this with respect to p. So if we integrate, we will get y naught p, because there is no p here. Here p square upon 2 delta y naught, and here like if you multiply this p inside, it is p square minus 1, and integration of p square minus 1 is p square minus p is p cube upon 3 minus p square upon 2, and this factorial and this delta 2 y naught is we keep here. Similarly, third term we have this one, like when we multiply p into p minus 1 and p minus 2 and integrate with respect to p, we will get this one. So like this we are getting. Now if you can see in here, like each and every term containing p. So if I substitute the lower limit, p equals to 0, this is whole thing is 0. And when I substitute p equals to n, I will get this one. H into n y naught plus n square upon 2 delta y naught, n cube upon 3 minus n cube upon 2 factorial delta 2 y naught, and like this. So this integration we will have equivalent to this one. Now we can see that this n is common each and every term. We have taken this n is out. So we have y naught plus n by 2 delta y naught, n square over 3 minus n upon 2 factorial delta 2 y naught, like this we are getting. So this is known as the Newton-Cotes quadrature formula. Like if I take LCM here, so after taking LCM and taking n out also, I will have this n into 2n minus 3 upon 12. Similarly, after simplification, we have this here.
Okay. Is it okay? Hello. I think
So this is our Newton quadrature, Newton-Cotes quadrature formula. This equation 1. So this you have to remember for whatever purpose. For problem solving, this is, we will not remember this one. So this is known as Newton quadrature formula. Based on this formula, we develop different formula. So here what is I? Here I is actually this one, integration v y dx. So the value of this integration is given by this Newton-Cotes quadrature formula. So now we develop first formula known as the trapezoidal formula. With the help of this Newton-Cotes quadrature formula. So how we do this? What we do in this trapezoidal formula, we divide the given interval integration AB. This is a given integration AB into sub integration. You can see, like I have chosen equally spaced point x0, x1, x2, x3, xn minus 1. And then I can obviously write this integration into sub integration, like sum of these sub integrations: x0 to x1 y dx, x1 to x2 y dx, xn minus 1 to xn y dx. So first thing I have to do this one. The next thing is like here with this x0 to x1. So here is only one interval, you can see that. So now I approximate only this part by using our Newton-Cotes quadrature formula. So if I use Newton quadrature formula to calculate this part, similarly I calculate this part separately using the Newton quadrature formula, and similarly this one. So how we will do this one? You can see this is x0 to x1 y dx. So I1 is x0 to x1 y dx. So now you can see in the Newton quadrature formula we have this one. So this formula is applicable when we have divided the given integral into n subintervals. And here n is representing the number of subintervals. But here we have only one interval. So like in I1 you have to, like we have x0 to x1 y dx. So here we have one interval. So one interval, so it means I have to substitute n equals to 1 in this formula. So I will substitute n equal to 1 in this formula. Next thing is that because here, so like you have to think like that, I am not approximating this integral directly using the Newton quadrature formula. I am not approximating this interval directly using the Newton quadrature formula. What I am doing, I am splitting this interval into n subinterval, and then each subinterval I am approximating using this Newton-Cotes quadrature formula. So this sub interval I am approximating using this Newton-Cotes quadrature formula. So here x0 and x1 are 2 points. So one theorem I already told you, that if I am having n plus 1 data points, so it means that I can fit a polynomial of degree n. And if I am able to fit a polynomial of degree n, it means that the n plus 1th higher order forward differences are 0. So here I am having only 2 points. So 2 points means n equals to 1. So it means I am able to fit a polynomial of degree 1 in, because I am having only 2 points. One is x0, another one is x1. So it means I am having 2 points. It means I am able to fit a polynomial by using Newton forward interpolation formula of degree 1 only. So if the polynomial is fitted is of degree 1, it means its first forward difference, this delta y0 is non-zero, or it may be constant or it may be 0. But higher order forward difference like delta 2 y0, second order forward difference of y0, third order forward difference of y0 are 0. So all of them are 0, because I am having only 2 points. One is x0, another one is x1. It means I am able to fit a polynomial of degree n. It means its first order forward difference is constant. Constant may be 0 or may not be 0, but second and higher order forward differences are definitely 0. So in this Newton-Cotes quadrature formula, this highlighted terms are 0. So if these highlighted terms are 0, so I am having only this much formula. And then in this much formula, I substitute n equals to 1. So because I am taking only one interval, x0 to x1. So if I substitute n equals to 1, I am having this one. You can see 1 into h, y0, because n is 1, so 1 by 2, and delta y0. And these all 0 because I am taking only 2 points. Now, delta y0 is, from the definition of delta y0, it is y1 minus y0. because y naught y at x naught plus h minus y at x naught, that is y1 minus y. So simplification h upon 2 y naught plus y1. Now the second one, the second interval I see x1 to x2. So here again you can see I am having only 2 points. One is x1, another one is x2. So one is x1, another one is x2, but now the initial point is x1 instead of earlier it is x0. So now I approximate the same I2 interval integral, because it's containing 2 points, so it means again here these all are 0. So I am having only that much formula. But the problem here, now the initial point is replaced in this interval by x1. So if the initial point is replaced by x1, so obviously this y0 is replaced by y1, and this is actually delta y1. So this is 1 into h y1 plus 1 by 2 delta y1. And the definition of delta y1 is again y2 minus y1, and after simplification, I am having h by 2 y1 plus y2. Similarly for this x2 to x3. So for x2 to x3 again it's a 2 point I am considering, and I am approximating this with this formula, but being 2 points in consideration, this thing are 0. And as the initial point in the I3 is x2, so this y0 is replaced by yx2 or delta y2. So we have this one. And after like substituting the value of delta y naughts, I am having this. So in general, in IN, I am having yn h by 2 yn minus 1 plus yn. So now I add all these approximation of I1, I2, I3, because I is actually I1 plus I2 plus I2 plus IN. So like this I substituted, this is I1, I have calculated here, I2 here, I3 here, and IN here. So the integration a to b fx dx is equals to I, and that one is equals to this one. So a to b y dx, so since h by 2 is common in all the terms, so h by 2 here. So y0 is coming only one time. Similarly, yn is coming only one time, so I have collected them together like y0 plus yn. Now y1 is coming here also and here also. Similarly, y2 come here in the next step also. So 2 times of y1 plus y2 plus yn minus 1. So this is known as trapezoidal rule. So if I ask you to find the integration using trapezoidal rule, you have to use this one, because some authors or some books you will find they will say this is also trapezoidal rule, but this is actually trapezoidal rule, but we are not using this one. In general, people use this one. So this is actually trapezoidal rule, because, or we say that it is generalized trapezoidal rule. So this generalized trapezoidal rule you have to use to solve the problem when I ask you to solve the integration by trapezoidal rule, and you have to use this, you have to remember this formula for viva purpose also and for numerical purpose also. H by 2 y0 plus yn plus 2 times of y1 plus y2 plus yn minus 1. So like we have one problem. So like I told you earlier, like in the, like I have to evaluate this integral, even though it is e raised to power x, and you know that the integration of e raised to power x is e raised to power x, and you can substitute lower and upper limit. But if someone did this kind of thing, like they have analytically solved this and say that sir I have got the answer, they will get 0, because I am explicitly right in the examination time you have to solve this by using this method, by the trapezoidal or some any other method, and you have to solve this numerically, not analytically. If you solve analytically, you will simple function e. So here y is equals to e raised to power x, because it is given here explicitly. Now I have to identify my a is 0. So whatever a is, I say it is my x naught. Then I have to say what is b, upper limit is b, that is 1.2. So I say it is my x1. And now I have to take n, because I have to divide the integral this into n subintervals. So here I am taking 6. You can take 9 also, you can take 10 also. So it's depending on you, but for understanding purpose, now I am taking only 6. So n equals to 6. Even though sometimes in a exam I write the divide the interval a b into 6 subinterval and then use the trapezoidal rule. So here n equals to 6. So if n equals to 6, you have to identify h. So what is h? The formula for calculating h is b minus a upon n. So here b is, that is upper limit 1.2, a is lower limit 0, and divided by n, n is 6. So finally your h is 0.2. So now you, because this is not given to you, because the explicit form of fx is given, so you have to construct this also by yourself. So like if this is your x naught, so x naught is 0. So what is the value of y naught? You substitute x equals to 0 in e raised to power x, you will get e raised to power 0 and you will get 1. Now what is x1? The formula for x1 is x naught plus h. X naught is 0 and h is 0.2. So 0 plus 0.2 is actually 0.2. So your x1 is 0.2. And now you use your calculator to calculate e raised to power 0.2, and this is the value. Now what is x2? x2 is x naught plus 2h. X naught is 0. 2 into h. 2 into h, it means 2 into 0.2, it means 0.4. So you have x2 as 0.4, and then you calculate e raised to power 0.4 using your calculator, you will get this one. So this thing you have to create. So this is like our n equals to 6 here. So this is your x naught and this is your xn, even though you can say it is x6. So this is xn, x naught, this is xn, this is y naught, this is yn. This is yn, or you can say y6 also. So what is trapezoidal rule? It's a simple one, h by 2. ये यहाँ पे गलत लिखा है, ये h की जगह y होगा. Okay. This one is wrongly written here. It is not h, it is y. Y naught plus y6, because you know the formula trapezoidal now, y naught plus yn. So here yn is y6. So y naught plus yn is 6, plus 2 times of y1 plus y2 plus y3 plus y4 plus y6. H is 0.2, 0.2 upon 2. You have this. Now you have to substitute what is the value of y naught. It is 1. So you have substituted this. What is the value of yn or y6? It is this one. You substituted here. 2 times of what is y1? This is y1. And what is y2? So this is y2. What is y3? This is y3. What is y4? This is y4. And what is y5? This is y5. So you have substituted all the values, you use your calculator, and this is the value of the integration 0 to 1.2 e raised to power x dx. So this is the final answer. Now we have another method known as Simpson 1/3 rule. It is not here. Okay, we will see in some areas. I think this is again visible. Okay, so we have already discussed this numerical integration. This is Newton-Cotes quadrature formula. In this we have a to b, and then we have chosen n equally spaced point. You can see like this is x naught plus nh, x naught plus 2h, and x naught plus nh. And here we have calculated the value of y at x naught, y1, y2, yn. So this is our like a polynomial. So we first write here they have used the variable r instead of u. So So you can see it is actually our Newton forward interpolation formula. This here R is actually x minus x naught upon h. So you after integration you will get this, and we have already simplified all this thing, and finally we have our quadrature formula. This one, a to b, here a actually x naught and b is xn, and xn is x naught plus nh, and this is the Newton Cotes quadrature formula that we have already derived. So like in trapezoidal rule, what we do, where we divide the integration into n subintervals like this. This is I1, this is I2, this is In, and for I1 we have already calculated h by 2 y0 plus y1, h by 2 y1 plus y2, and like this, and finally this is known as the trapezoidal rule. Now we go to the Simpson one-third rule. So in Simpson one-third rule, we divide the given integral like a to b, it is given to us, and we divide the given integration into even number of sub integration. You can see here x naught 2x naught plus 2h, then x naught 2h plus 2, x naught plus 4h. So like this. Then x naught plus n minus 2h2, x naught plus nh. So we have to divide the given interval a to b. A means x naught and b is like x naught plus nh. So we have to divide this given interval, given integration into n even sub integrations. So like this. So now the first integration, you can say now this is my I1. So this is I1 containing one point, it's containing x naught, because there is another point na x1 lies in between, which is x naught plus 1h and x naught plus 2h. So now in this I1 we are taking 3 points. One is x naught, another one is x1, another one is x2. So if we are taking 3 points, one is x naught, another one is x1, and another one is x2, 3 points means we are able to fit a polynomial of degree 2. So if we are able to fit a polynomial of degree 2, it means that the second order forward difference is constant and third and higher order forward differences are 0. And here in each I1, I am taking two subintervals. You can see one is x0 to x1 and x1 to. So this x0 to x plus 2h, I am having two subintervals. So now I am going back to our Newton Cotes quadrature formula, and in that formula I have to put n equals to 2. So this nh, you can see this is, I have substituted n equals to 2. Since I am taking 3 points, it means second order forward differences is constant and higher order forward differences are 0. So here you can see in this Newton Cotes quadrature formula, because now I am taking in Simpson one-third formula, I am taking n equals to 2. So we will take the term up to here, because 3 point, it means second degree polynomial, it means delta 2 y0 constant and higher, and these are zeros. So all the terms are 0. So we considering only these term, and in this term I am substituting n equals to 2. So if I am substituting n equals to 2, it is like 2 into h y0, 2 upon 2, that is 1 into delta y0, 2 into 4 minus 3, that is 1 upon 12. So 2 upon 12, that is 1 upon 6. So finally I am having here y0 plus delta y0 plus 1 by 6 delta 2 y0. You can see here y0 plus delta y0 plus 1 by 6 delta 2 y0. And now what we do, we expand this. Delta y0 is y1 minus y0, and delta 2 y0 is like y2 minus 2 y1 plus y0. And after simplification I am having this. Similarly, I go for I2. I2 is now having x0 plus 2h, that is starting from x2, and x3 and x4 is this one. So it means now my initial point is transformed from x0 to x2. So now it is y naught is replaced by y2, and similarly other things you will get this one. In general, for nth subinterval I am having this one. So now I add this I1, I2 and In integral values to get my final value. So this is, so I can see here again in I1 I am having y naught, and y naught is not coming in any1. So y naught is here. Similarly in In I am having yn is not coming in anywhere else. So this is y naught plus yn. Now you can see that the odd terms, like here we are getting y4 into y1, here I am getting 4 into y3, and here I am getting 4 into yn minus 1. So I am collecting all these terms which having 4 as a multiple like this. So the odd order index is like this: 4 into y1 plus y3 plus yn minus 1. Now y2 coming here also and in the next one also. So it means 1 plus 1. Similarly, y4 comes here also in the next one also. So y2 is coming 2 times. Similarly, y4 is also coming 2 times in this addition. So it is like 2 times of y2 plus y4 plus yn minus 2. So this is known as the Simpson one-third formula. So in this Simpson one-third formula, we have h by 3 y naught plus yn plus 4 into y1 plus y3 plus yn minus 1 plus 2 into even terms y2, y4, yn minus 2. So here you have to remember one thing, that you have to choose your n always even. Now you cannot choose your n as 5 or 3. You have to take your n as a even though this is a question of Viva also, like how we choose the subintervals in case of Simpson one-third formula. So you have to tell me that this, sir, we have to choose n as even. So like this. So we'll see one problem related to this. So this is Simpson one-third formula, a to b y dx. So h by 3 y naught plus yn plus 4 times odd indexes plus 2 times even indexes. So now this is the integration, like I have to do 0 to 1. So 1 upon 1 plus x dx. So this is, I have to calculate. So here a is obviously in lower limit 0, b is upper limit 1, and n is 6. I have to taken care that I cannot take 5 or 3 here. So if I have taken 5, that means my results are wrong. Always in trapezoidal there is no rule. You can take 3 also, 5 also, or 6 also. But in Simpson you have to take even. So what is b? What is h? H is b minus a upon n. So here b is 1, a is 0, n is 6. So b minus a upon n is 1 upon 6. That is this one. So this is your x naught. X1 is x naught plus h. So x naught is 0, h is 1 by 6. So x2 is x naught plus 2h. X3 is x naught plus 3h, 4h, 5h, and 6h. That is 1. Then we have to calculate the value of y1. So I have to substitute here x equals to 0. If I substitute x equals to 0 here, that is 1 upon 1. Now I have to substitute x equals to, because I want to know what is y1, so I have to substitute here 1 by 6. So this is 1 upon 1 plus 6, 6 upon 7. To calculate the value of y at x2, I have to replace this x by 2 by 6. So 1 upon 1 plus 2 by 6, finally 3 by 4. So their numerical values are given here, and the formula is this. Because here we have taken 6, so yn is our y6. So y naught plus yn, then 4 into this y1, y3, and 2 into y2, y4. So this is like you can see here 1 upon, because h is 1 upon 6, in the formula it is 1 by 3, 1 h upon 3. So h is 1 by 6, 3 is all in the formula. This is y naught, so we have substituted here, and this is like 0.5. It is not visible here, but it turns out to be 0.5. You can see now, like you substitute 1 upon 1 plus 1, so 1 by 2, it turns out to be 0.5. So y naught plus y1, then 4 into y1, this is y1, then y3, 2 by 3, so this is y3, and then y5. 4 into y1, y3, y5. Then 2 into y2. This is y2 and this is y4. And then you use your calculator. So this is the value of integration this using the Simpson 1/3 formula. So in exam, I explicitly written this thing that you have to solve this integration using Simpson 1/3 formula or using Simpson or using trapezoidal formula. Now the next formula is Simpson 3/8 formula. So how you derive this formula? Like now we take 4 points in Simpson 3/8 formula. This I think we'll discuss tomorrow. So I have to stop here. If you have anything to ask, you can ask. Otherwise, I will take the attendance. So roll number 1,
Present, sir.
2,
Present, sir.
3, 4,
Present, sir.
5, 6, 7, 8, 9,
Present, sir.
8 and 9 present, 10,
Present, sir.
11, 12,
Present, sir.
12 present, 13,
Present, sir.
14,
Present, sir.
15,
Present, sir.
16, 17,
Yes, sir.